Let's carefully analyze a specific, easily understood modern-day scenario that questions the widely accepted belief that the Earth is a spinning globe. By examining one example in detail, we aim to present compelling evidence that the Earth is in fact stationary. Instead of briefly touching on multiple contemporary examples that may lack overall depth and impact, we will concentrate on one particular example that clearly evidences the Earth's fixed and stationary nature. Our primary objective is to cast significant doubt on the credibility of the mainstream narrative endorsed by NASA and the conventional principles of flight dynamics that posit the theory of a rotating spherical Earth. Through this detailed examination, we aim to reveal how easily the public continues to accept official explanations without substantial scrutiny. We will refute these commonly accepted explanations, highlighting their inherent flaws and lack of plausibility when examined closer. In our analysis, we will focus on round-trip flights between Atlanta, Georgia, and San Diego, California. These coast-to-coast flights typically cruise at an average speed of 550 miles per hour and have an average flight duration of approximately 3.45 hours, assuming no wind or turbulence. 1,900 miles divided by 550 miles per hour equals 3.45 hours. This should raise obvious and critical questions. At this latitude, considering that the Earth is said to rotate west to east at 870 miles per hour beneath the plane during flight, how do flights in both directions report nearly identical flight times? In other words, if a plane flies at a constant speed of 550 miles per hour between these two cities, how can the flight times be the same in both directions, given that the Earth is said to rotate from west to east, moving with the plane in one direction and directly against the plane in the other? Examining closer, on an eastbound flight from San Diego to Atlanta, the Earth's rotation moves in the same direction as the aircraft. Conversely, on a westbound flight from Atlanta to San Diego, the Earth rotates in the opposite direction to the aircraft's travel. These opposing dynamics present significant challenges that become apparent upon closer examination. In our first scenario, when heading east, once our plane is airborne and detached from the Earth's surface, it leaves San Diego heading for Atlanta. The Earth is said to rotate eastward below our flight with us at 870 miles per hour, while our plane eventually reaches its own independent cruising speed of 550 miles per hour. How then will our plane ever arrive in Atlanta? To clarify, our plane's cruising speed of 550 miles per hour is 320 miles per hour slower than the Earth's rotational speed of 870 miles per hour beneath us during our flight, as the Earth's direction of spin and our plane are heading in the exact same direction and latitude. In our second scenario, as we begin our return flight to San Diego from Atlanta, the dynamics change entirely, further complicating the official explanations as to why the flight times in both directions are almost identical. Once the aircraft lifts off and disconnects from the Earth's surface, San Diego is now approaching our plane at a speed of 870 miles per hour due to the eastward spin of the Earth bringing San Diego directly to us, while simultaneously directly approaching San Diego, our destination city, at an independent flight speed of 550 miles per hour. Our plane and San Diego are now closing in on each other. This should, in reality, significantly reduce our flight time, as the two combined speeds effectively create a far faster convergence speed of 1,420 miles per hour. The actual flight duration should now be shortened to just 1.33 hours, rather than the actual 3.45 hours observed daily for this specific flight. 1,900 miles divided by 1,420 miles per hour equals 1.33 hours. The fact that the actual daily flight times between these two cities are almost identical in both directions, assuming no wind or turbulence, should clearly reveal that the Earth does not rotate, but rather rests. The first counter-argument within the official narrative attempts to explain the identical flight times between these opposing scenarios by invoking the principle of conservation of momentum, a fundamental concept in physics. According to this explanation, when our plane flies from San Diego to Atlanta, it retains the eastward spin imparted from the Earth's rotation at takeoff, which is approximately 870 miles per hour at this latitude. The plane is then said to add its own separate cruising speed of 550 miles per hour to this conserved momentum. Therefore, the plane's total airspeed is said to be a combination of the 870 miles per hour imparted by the Earth's rotation at takeoff and its own cruising speed of 550 miles per hour. In effect, the plane is then alleged to be moving at a total airspeed of 1,420 miles per hour. 870 miles per hour plus 550 miles per hour equals 1,420 miles per hour. How does an airplane, once airborne and detached from the ground, maintain the momentum it is said to inherit from the Earth's rotation at takeoff during its flight to Atlanta? Consider a baseball being thrown from west to east, similar to an airplane. Does it continue on its initial trajectory unchanged, or does it begin to arc towards the ground due to gravity and air resistance almost immediately? Conventional wisdom tells us that a baseball will indeed begin arcing downward. Would an airplane not be subject to these same principles? The continuing argument to this states that an airplane maintains its initial velocity inherited from the Earth's rotation at takeoff through continuous propulsion from its engines, which counteracts any slowdown. However, we must remember that once an airplane leaves the ground, it is no longer propelled by the force of a spinning Earth. Additionally, air resistance acting against the plane, increasing with speed, continually works against any initial velocity boost provided by the Earth's rotation. The net result is that once airborne and disconnected from the ground, the airplane's forward motion relies solely on engine thrust to maintain the required speed of travel. This is because any initial contribution from the Earth's rotation at takeoff is soon negated by continual air resistance. To further support this, it is important to recognize that passengers on commercial flights are never informed that they are traveling at speeds upwards of 1,420 miles per hour to counteract the Earth's rapid rotation during some flights. We never hear relative motion mentioned or referenced at any point, past or present, concerning commercial flights. The only speed ever mentioned is the ground speed, which is typically around 550 miles per hour, or slightly higher with a tailwind. It should be quite apparent that the plane maintains an airspeed and ground speed of 550 miles per hour in both directions, which supports the consistent flight times observed for these daily flights, aligning perfectly with the scenario of a non-rotating Earth beneath it. A stationary Earth logically explains identical flight times in both directions, eliminating the need for the adjustments and complex explanations required for a spinning Earth. In summary, the concept of conservation of momentum proves ineffective in our scenario once the plane becomes airborne. Although the airplane would theoretically inherit an initial burst of momentum from a rotating Earth at takeoff, this momentum is quickly negated by air resistance and gravity. Once airborne, the plane operates as an independent entity, with external forces continuously counteracting any inherited momentum, effectively nullifying the predicted effects of the conservation of momentum principle. The second common counterargument suggests how gravity and friction cause Earth's atmosphere to rotate in conjunction with the Earth. This argument states that airplanes are transported not only by the previously mentioned conservation of momentum, but also by the air, which is itself influenced by Earth's rotation. It implies that the Earth, its atmosphere, and the airplane move together as a single system. According to this claim, in our scenario, the airplane maintains the 870 miles per hour speed it initially gains from the Earth's rotation thanks to atmospheric cohesion. This cohesion is alleged to help the airplane preserve and maintain the speed inherited from the rotating Earth at takeoff. Subsequently, the airplane's engines are said to provide the additional thrust needed to reach the higher speeds which are required for progress towards Atlanta. For this theory to be valid, it must account for the scenario where an airplane turns off its engines mid-flight. In such a case, the airplane would need to be significantly carried along by the atmosphere, thereby supporting the claim of the atmosphere's significant role in this case. However, common understanding tells us that, much like a thrown baseball, an airplane in this scenario would immediately begin to descend. This illustrates that atmospheric drag does not significantly influence its forward momentum to help sustain its flight. Next, the idea that atmospheric drag, a form of cohesion, could attach to and sustain the momentum of a commercial airplane weighing between 500,000 and 1,000,000 pounds by dragging it along, is beyond difficult to accept. Such theories and explanations seemingly require us to disregard logic, common sense, and reason to consider them feasible. The concept of atmospheric drag is quite often compared to a boat being carried by a river's current. However, this analogy quickly falls short upon closer examination, recognizing that water has significant density and cohesive properties that air simply does not match. Given air's considerably low density and minimal cohesive potential, the idea that it could mimic the cohesive behavior of water, adhering to and carrying along an extremely heavy, compact object like a commercial airplane, is fundamentally flawed. To demonstrate a valid example of atmospheric drag, consider the observable phenomenon where a cigarette smoke appears stationary and aligned inside a moving car with closed windows and inactive air vents. This occurs because both the air inside the car and the cigarette smoke share similar properties of density and buoyancy. As a result, when the car moves, the entire body of air inside, including the smoke, moves uniformly with it. This is a valid example of atmospheric drag. Now consider a scenario where a ball is tossed upward inside a moving car. If the brakes are abruptly applied while the ball is still in mid-air, the ball would trend forward toward the dashboard or windshield. This phenomenon demonstrates that the atmosphere inside the car does not significantly adhere to the ball and slow its forward momentum to match the rapidly decelerating vehicle's internal atmosphere. Even if there is a slight effect, it is far too negligible to be noticeable. This example with a ball illustrates that low-density air does not substantially adhere to or considerably affect denser objects. This observation directly challenges the notion that air can adhere to a denser object, such as an airplane, and significantly contribute to dragging it along in a moving atmosphere. Despite this evidence, we are expected to believe that an airplane, with its considerable density and weight, can be effectively carried along by atmospheric drag, maintaining the momentum acquired from the Earth's rotation at takeoff. While atmospheric drag might have a brief effect, it is not substantial enough to significantly influence the behavior in our airplane scenario, thus rendering it a negligible factor. It is surprising to see even prominent, highly intelligent individuals attempting to justify atmospheric drag and conservation of momentum as plausible explanations for consistent flight durations observed in our two flight scenarios. It would not be surprising if quantum mechanics were introduced at some point in the future as yet another means to further perplex and confuse us. Our tendency to readily accept scientific explanations or passively conform to official narratives highlights an enduring pattern within society. Revisiting the application of Occam's razor to our flight scenarios reveals that the simplest explanation is clearly a stationary, non-rotating Earth. This model plausibly explains why flights between the east and west coasts have nearly identical times, with no need for complex explanations, adjustments, or fixes required by a spinning Earth model. The official explanation from NASA and the field of modern flight dynamics, attempting to account for these identical flight times despite an allegedly spinning Earth, is entirely untenable.